What's up, coders? Have you ever been stuck on a problem that makes your head spin, like how to zigzag through a binary tree? Well, you're not alone. Today, we are tackling a popular coding challenge, Zigzag Order Traversal. If you're aiming to ace that coding interview or just want to level up your skills, this one is for you. When I first tackled this, I tried the brute force approach, and let me tell you, I got tangled in loops and if else statements. It was a mess, but then I discovered a simpler way using a queue and a little logic to reverse the order when needed. Trust me, once you see this code, it'll click you as well. Here's the challenge. You're given a binary tree and you need to traverse it level by level, but with a twist. Instead of always going left to right, you alternate direction. Let's see it in an example. Here's the tree. You might be thinking, why does this matter? Well, zigzag traversals is super useful in scenarios like rendering hierarchical data in a unique visual pattern or even in AI decision trees. And plus, it's a fun way to sharpen your problem solving skills. Let's break it down into three simple steps. Use a queue to handle level by level traversal, use a loop, use a flag to determine the traversal direction, toggle the direction at the end of each level. Sounds simple, right? Alright. Now let's dive into the code and we'll see it in action. Let's walk through this code step by step. First, we define a method called Zigzag Level Order. This method takes the root node of a binary tree as input and return a list of lists where each inner list contains the node values of a specific level in zigzag order. Here we initialize an empty list called result. This will store our final output, the zigzag level order traversal of a binary tree. Next, we handle a simple edge case. If the root of the tree is null, we return an empty list. No node to traverse, so no further processing needed. Now we initialize a queue for level order traversal and add the root node to it. This queue helps us process nodes level by level, which is crucial for zigzag traversal. Here we set up a boolean flag called left to right and initialize it to true. This flag determines the order of traversal for each level when it's true. We'll always add node values from left to right, and when it's false, we'll reverse the order and go from right to left. Now we enter a while loop that continues as long as the queue isn't empty. This ensures we process all levels of order one by one. At the start of each level, we store the number of nodes in the current level using level size. This tells us how many nodes we need to process before moving to the next level. Then we create an empty list called level list. This will store the node values for the current level in the appropriate zigzag order. Next, we use a for loop to iterate through all the nodes at the current level. This loop runs level size times, once for each node in the level. Inside the loop, we dequeue the next node from the queue. This is the node we are currently processing. Now comes the zigzag logic. If left to right is true, we add the node value to the end of level list. Otherwise, we insert it at the beginning, reversing the order from right to left traversal. Next, we enqueue the left and right tree of a current node. If they exist, this will be processed in the next level. Once all nodes at the current level are processed, we add level list to result. This completes the zigzag traversal for this level. And finally, we toggle the left to right flag to switch the direction for the next level. If it was true, it becomes false and vice versa. Once all levels are processed, we return the result. This contains the zigzag level order traversal of the binary tree. And that's it, a clean, efficient solution, easy to understand. By breaking the problem into manageable steps, we have created a zigzag traversal that works seamlessly for any binary tree. Great job. Notice the direction changes with each level, left to right on one level and right to left on the next. This simple toggle makes all the difference. And here's a quick tip. Instead of reversing the list at the end of each level, inserting an index 0, that is during right to left traversal, saves times and makes your code more efficient. And that's a wrap, folks. You just unlock a powerful technique for binary tree reversal. If you found this helpful, smash that like button, subscribe for more coding deep dives, and let me know in the comment what problem should we tackle next. Keep coding, keep growing, and I'll see you in the next one.